Welcome to this session. In the previous session, we saw how to find the homogeneous solution of a recurrence relation while using the methods of characteristic roots. In this session, we will talk about the other part of the solution, that is the particular solution. If suppose we have a recurrence relation like plus C2 an minus 2 and so on plus ak cn minus ck an minus k is equal to fn. If this is a linear recurrence relation in constant coefficients where an minus 1, an minus 2, these are the recurrence terms, c1, c2, c3 up to ck, these are the coefficients. These are all constant coefficients. And this fn is a function that is representing or that is equal to this entire recurrence relation. Now, in order to solve this recurrence relation with the help of the method of characteristic roots, we said that the solution will be made up of two parts. One is called the homogeneous solution, for which we equate this function fn. We equate this function fn to 0. That means we only take the left hand side of the recurrence relation and we equate it to 0, and we find the homogeneous solution with the help of methods of characteristic roots. That is called the homogeneous solution. Right? We will now denote it by, let us say, ANH. The second part is when we actually consider the recurrence relation to be a non-homogeneous recurrence relation, and we will find the particular solution. So this will denote by ANP. And the general solution of the recurrence relation, which is denoted by AN, is the sum of the homogeneous solution and the particular solution. So last session we saw how to find the homogeneous solution. This session we will talk about how to find the particular solution of the recurrence relation. So let's start. Say, once again, if this is the recurrence relation where Ci as the constant and Fn is a function, first of all, we will find the homogeneous solution ANH by setting Fn is equal to 0, just I already mentioned. If you want some help regarding how to find out the homogeneous solution, I suggest you refer to the previous video that I have uploaded, the one where we found the homogeneous solutions. Once I have obtained the homogeneous solution, then I will look at the function Fn. Now we will consider the function Fn and we will find out the trial particular solution by using the proper trial function. Now the way to do this is, now I have the function Fn. Now this can be a simple constant, or it can be, let us say, 4 to the power n or 3 to the power n, or it might be a polynomial or something like that. So for each and every type of function, we have a specific trial function. Okay. Now this is a table of all the trial functions. Now I suggest that you pause this video at this moment and you note down all these trial functions. You note down this trial function for reference for solving the numericals that we will be talking about later. So pause this video here, make a copy of this trial function table, and then we'll proceed. Right? So I hope you have made a copy. Now let us see. These trial functions are identified on the basis of the function Fn. Fn, if you remember, is this part. In the recurrence relation, this is the Fn part, this part. Once I have identified the homogeneous solution, now I will use this Fn to identify the trial function. Now, if Fn is a constant, then the trial solution is also a constant. Right? If Fn is of the form b to the power n, if it is of the form b to the power n, where b is not a root of the characteristic equation, C stands for characteristic equation. Say for example, if the roots of characteristic equation are, let us say, 1 and 2, and let us say we are getting b as, let us say, 3, then this will be this particular case. So B is 3 where the roots are 1 and 2. So this will fall under this category. So b to the power n, where b is not a root of the characteristic equation, then the trial function will be of the form a b to the power n. If the characteristic root is of the form c to the power n, if it is of the form c to the power n, where c is a root of multiplicity s. Say for example, if these are the roots and I am getting the fn, let us say fn is 2 to the power n. If I am getting this, now this 2 is one of the roots. It is one of the roots. So this will be this particular case. So here this particular root is only occurring once. So the multiplicity in this case will be 1. Let's take another example, a simple example. Let us say the roots of the characteristic equation are 2, 2, 2. And then I am getting fn as 2 to the power n. In this case, 2 is a root of the characteristic equation with multiplicity 3. So this is the case. If this cn, if that function is of the form c to the power n, where c is a root of characteristic equation of multiplicity s, then the trial function will be of the form a0 n to the power s, where s is the multiplicity, and c to the power n, where c is the root. If the function fn is a polynomial of degree m, if it is a polynomial of degree m, then it will be, the trial function will be a0 plus a1n up to am n to the power m. Remember, m is the degree of the polynomial. Sorry. If the function fn is of the form b to the power n pn, remember b was a value which is not a root of the characteristic equation. So for a function of the form b to the power n pn, where b is not a root, we get the trial function as b to the power n and a0, a1n and so on. You remember, see, here I am multiplying two options over here. I am using two of the options over here, b to the power n, pn. So the trial function is also similar. We have b to the power n, and instead of a simple a, I am having this entire polynomial. So similarly over here I have b to the power n, a0 plus a1n up to this over here. Similarly, if the function is of the form c to the power n pn, where c is a root of multiplicity s, so see over here I had n to the power s, c to the power n, a0. So similarly n to the power s, c to the power n will remain the same, but instead of a0 I'll now have a0 plus a1n plus up to so on a to the power am n to the power m. So this is a table of all the trial functions. Now the use of these trial functions will become clearer once we handle certain examples, right? So the steps till now have been, first of all, step 1, find the homogeneous solution a and h by setting fn is equal to 0. Step 2, find the trial particular solution by using the proper trial function. Trial function you will find from this particular table. Now next, once you have identified the trial function, that brings us to the remaining steps. Now we have step number 3, substitute the trial particular function into the recurrence relation and find the undetermined coefficients and the particular solution. Now you remember, here when we talked about the trial functions, we were using the constants a or a0, a1, a2 and so on. Now they will be identified or they will be found out by substituting the trial particular function into the recurrence relation, and we will find out the value of the a or a0, a1, a2 and so on, and thus we will obtain the particular solution a and p. Then we find the complete or the general solution as an is equal to homogeneous solution plus particular solution. Now a very important point, where I have seen many times that students make mistakes. When we found out the homogeneous solution, usually in the earlier questions, when we found the homogeneous solution, immediately after that we used the initial conditions to find the value of the coefficients b1, b2, b3 and so on. But here we will use those initial conditions as a last step. Here, the initial conditions will not be used over here. The initial conditions will be used over here. So, find the constants in the general solution by using initial conditions. Now, let's do one thing. Let's solve a simple example so that it will become clearer. Now, the recurrence relation that has been given to us is yk minus 1 minus 6yk minus 2 is equal to minus 30, and the initial conditions are given to us as y0 is equal to 20 and y1 is equal to minus 5. So, first of all, we will have to find the homogeneous solution. So, for homogeneous solution, we have to know Fn is equal to 0, or in this case it will be Fk is equal to 0. This is our function Fk, right? Fk in this case is f of k is equal to minus 30. So now for homogeneous solution, we first put it to 0. So I get yk minus 1 minus 6yk minus 2 is equal to 0. Next step, I have to find out the characteristic equation. Find the characteristic equation. Now I'm going to find out the characteristic equation directly, because we have already seen how to find a characteristic equation in the previous session. But if you are having problems how to find the characteristic equation, I suggest you rewatch the previous video where we talked about homogeneous solution. So the characteristic equation of this particular recurrence relation will be, let us say, r square minus r minus 6 is equal to 0. This is the characteristic equation of the recurrence relation. So once I have obtained this characteristic equation, see, it is quite simple to find out the characteristic equation. The order of the recurrence relation gives me the order of the equation. See here, the order of this particular recurrence relation is 2. Largest coefficient minus smallest coefficient is 2. So it will be a quadratic equation. So if I take k minus 2, if I take this term to have to be the constant term, or r to the power 0, so this will obviously have this plus 1. So this will be r to the power 1, and this is as k minus 2 plus 2. So this will be r to the power 2. So now I have this characteristic equation. Now I have to solve the characteristic equation to find the characteristic roots. Now by solving this particular equation, I get r minus 3 to r plus 2 is equal to 0. This is the solution of this particular equation. So that means I have two roots over here, r is equal to 3 and r is equal to minus 2. So these are real and distinct roots. Real and distinct roots, right? We once again use the table that we have talked about in the previous session to find out the homogeneous solution, and we get yk homogeneous is equal to b1 3 to the power k plus b2 minus 2 to the power k, right? Although we have been given the initial conditions, but we are not going to use the initial conditions over here. We will delay this process of using the initial conditions to find out the constants to the very end of the solution. So now I have obtained the homogeneous solution. This is the homogeneous solution. Now I have to find the particular solution. So for finding the particular solution, what I am going to do is I am going to first identify the trial function. Trial function. Now we have seen the function f here is 30. That is a constant. So if you see the table over here, so for constant, the trial function is also a constant a. So the trial function yk is also a. This is the trial solution. Now what I am going to do is I am going to substitute this trial function into the recurrence relation, as this is a constant. So I'll get, substituting into recurrence relation, I'll get a minus 6a is equal to minus 30. As this is a constant, so it will make no difference whether it is yk or yk minus 1 or yk minus 2. This value will remain a only. So this is what I'll get after substituting it into the recurrence relation. So let's solve it further. So I get a minus 6a is equal to minus 30. Right? Solve it. You get minus 6a is equal to minus 30, or a is equal to 5. So this is the particular solution. Particular solution, YKP is equal to 5. Now general solution. Remember what was the homogeneous solution? Homogeneous solution was b1 into 3 to the power k plus b2 into minus 2 to the power k. This was yk homogeneous. This was the homogeneous solution, and this is the particular solution. General solution is yk is equal to yk homogeneous plus yk particular. That means I get b1 into 3 to the power k plus b2 into minus 2 to the power k plus 5. This is the general solution. Now we are going to use the initial values. y0 is equal to 20 and y1 is equal to minus 5. So 20 is equal to, I'll put k is equal to 0. 20 is equal to b1 into 3 to the power 0 plus b2 into minus 2 to the power 0 plus 5. So that gives me b1 plus b2 is equal to 15. So that gives me my first equation. Putting y1 is equal, k is equal to 1, I get minus 5 is equal to b1 3 to the power 1 plus b2 minus 2 to the power 1 plus 5. And this equation, this gives me my next equation, which says 3b1 minus 2b2 is equal to minus 10. So now I have two equations in two variables. This equation is in b1, b2. This equation is also in b1 and b2. So solving these equations, how do I solve these equations? I can simply multiply this equation by this. Let us call it equation number 1. Let us call it equation number 2. So what I can do is I can multiply the equation number 1 by 2 and add it to equation number 1. Let's do that. So I get 3b1 minus 2b2 is equal to minus 10, and let us multiply equation number 1 by 2. So that gives me 2b1 plus 2b2 is equal to 15. Let us add them. That this gets cut out. So I get 5b1 is equal to 5. So I get b1 is equal to 1. Sorry, I think I made some mistake. Okay, this will be, this will become 30, not 15, it will become 30. And so this will no longer be 5, this will be 20, and so this will be 4. b1 is equal to 4. Now I have b1 plus b2 is equal to 15. So I have obtained b1, that is 4, plus b2 is equal to 15. So b2 is equal to 11. So now I have the values of b1 and b2. So now the solution to the recurrence relation will be yk is equal to 4 into 3 to the power k plus 11 into minus 2 to the power k plus 5. This is the solution to the recurrence relation. Let's see another example. an minus 6an minus 1 plus an minus 2 is equal to 3 to the power n, and once again two initial conditions have been given, right? So first of all, let us find the homogeneous solution. For homogeneous solution, we will put this function fn. In this case, f of n is equal to 3 to the power n. So what we'll do is we'll put this function fn is equal to 0. So for homogeneous solution, I have an minus 6 an minus 1 plus 8 an minus 2 is equal to 0. This is my homogeneous recurrence relation. So now I find the characteristic equation. Characteristic equation using the similar method as I discussed in the previous question. I get r square minus 6r plus 8 is equal to 0. Solving this, I get r minus 2 and r minus 4 is equal to 0. So I get r is equal to 2 and 4. Once again, real and distinct roots. So the homogeneous solution ANH is b1 2 to the power n plus b2 4 to the power n. So this is the homogeneous solution. Now next we have to find the particular solution. For particular solution, now fn is equal to 3 to the power n. Now let's go back to the table. Now 3 to the power n, the roots are 2 and 4. The roots are 2 and 4 and the function is of the form 3 to the power n. That means this is the case. We have this case. So b to the power n. So the trial function is a into b to the power n. So using it over here, I get the trial function n, trial homogeneous function as a into 3 to the power n. So now what we are going to do, we are going to substitute this a into 3 to the power n in the recurrence relation. Now please check, see, as this trial solution is having an element n. So while substituting, you have to pay a little bit attention. So substituting in recurrence relation, I get, sorry, not y, an particular is equal to, now see, the first term is an. So what I get is a into 3 to the power n. The second term is minus 6 an minus 1. So an minus 1, a is a constant, it remains a, but an minus 1 now becomes 3 to the power n minus 1. See what I have done over here? For an, I used 3 to the power n, a 3 to the power n. For n minus 1, I had to make this n also n minus 1. So similarly, I get plus 8 a 3 to the power n minus 2 is equal to 3 to the power n. Right? Now, solving it, I can write it as a into 3 square into 3 to the power n minus 2 minus 6 a into 3 to the power n minus 2 plus 8 a 3 to the power n minus 2 is equal to 3 to the power 2, 3 to the power n minus 2. Now if I divide this entire equation by 3 to the power n minus 2, I get 9a minus 18a plus 8 is equal to 9. So solving it, 9 plus 8, 17 minus 18. So minus a is equal to 9, or a is equal to minus 9. So now the particular solution is ANP is equal to minus 9 into 3 to the power n. This is the particular solution. Let's put a bracket over here so that there is no confusion. So this is the particular solution. Now what we are going to do is we are going to find the general solution. An is equal to An homogeneous plus An particular, that is b1 into 2 to the power n plus b2 into 4 to the power n plus minus 9 into 3 to the power n. Now we are going to use these initial values. Now putting n is equal to 0, a0 is equal to 3 is equal to b1 into 2 to the power 0 plus b2 into 4 to the power 0 minus 9 plus minus 9 into 3 to the power 0. So that means I get the equation b1 plus b2 minus 9 is equal to 3, or I get b1 plus b2 is equal to 12. This is the first equation, equation number 1. Putting n is equal to 1, I get a1 is equal to 3, that is b1 into 2 plus b2 into 4 plus minus 9 into 3. Sorry, it was 7 over here, a1 is 7. So I get 2b1 plus 4b2 minus 27 is equal to 7, or it now becomes, the equation is 2b1 plus 4b2 is equal to 27 plus 7 is 34. This is my equation number 2. Right? So solving these two equations, now I'm sure you can easily solve these equations. This equation can be rewritten as b1 plus 2 is equal to 17. Right? This can be equation number 2. Now I'll simply divide this entire equation by 2. So this is now a new equation 2. This is my equation 1. If I subtract equation 1 from equation 2, it will give me b2 is equal to 5. And using b2 is equal to 5 in equation number 1, it will give me b1. It will give me b1 is equal to 7. So the solution of the recurrence relation will be an is equal to 5 into 2 to the power n, 7 into 2 to the power n plus 5 into 4 to the power n plus minus 9 into 3 to the power n. This is the solution to the recurrence relation. Right? Let's see another example. This is going to be a slightly longer example. Here ar plus 2 minus 5ar plus 1 plus 6ar is equal to r plus 1 whole square. Now notice something, we have not specified any initial conditions over here. If initial conditions are not given, that means the final solution is going to be in the terms of b1, b2, b3, the coefficients that we are going to find out in the homogeneous solution. So once again, here the function fr is of the form of r plus 1 whole square. That means r square plus 2r plus 1. That means this is, if I go back, this is a polynomial of degree 2. This is a polynomial of degree 2. So that means this is going to be my trial function. Right? So coming back to the question. Now, first of all, we have to find the homogeneous solution. For the purpose of homogeneous solution, we'll write the characteristic equation. Homogeneous solution, let us first write the homogeneous recurrence relation. That will be ar plus 2 minus 5ar plus 1 plus 6ar is equal to 0. So the characteristic equation will be r square minus 5r plus 6 is equal to 0. Solving it, I get r minus 2 to r minus 3 is equal to 0. So r is equal to 2 and 3. Once again, real and distinct roots. So ar homogeneous is equal to b1 into 2 to the power r plus b2 into 3 to the power r. So this is the homogeneous solution. Now, for the particular solution, we just saw that this function is a polynomial of degree 2. So the trial function will be ar, particular trial function is a0 plus a1r plus a2r square. We saw that as this is a polynomial of degree 2, so it will be, the trial solution will be also of a polynomial of degree 2, right? So now what I am going to do is I am going to substitute this trial function. I am going to substitute this trial function in the recurrence relation. Substitute in the recurrence relation. Substituting it over here, I get, see, I have the first term ar plus 2, right? Ar plus 2 means I'll have a0 plus a1 r plus 2 plus a2 r plus 2 whole square. Let's use two different types of brackets over here. So this is what I get when I substitute this in the recurrence relation term ar plus 2. Now the first term is minus 5ar plus 1. So I get minus 5 a0 plus a1 r plus 1 plus a2 r plus 1 whole square plus 6 a0 plus a1r plus a2r square is equal to r plus 1 whole square. This is what I get by substituting the trial solution in the recurrence relation. Right? Now what all I have to do is I'll have to expand this entire thing. So I'll be getting a0 plus a1r plus 2a1 plus a2r square plus a2 4 plus a2 4r minus 5 a0 plus a1r plus a1 plus a2r square plus a2 plus 2 a2r plus 6 a0 plus a1r plus a2r square is equal to r square plus 2r plus 1. Now, after this looks very intimidating, but don't worry, it is not as difficult as it looks like. Now, on the right hand side, I have terms that are involving r square, I have terms that are involving r, and I have terms that do not have any r in it. On the left hand side also, if you see, I have terms that involve r square. See, r square. I have terms that involve r. See, r, like this r, and so on. And then I have terms which do not have any r term in it, like this a0 and like this 2a1 and so on. So all I have to do is equate the three different types of terms. So equating, right? So I get a0 minus 3a1 minus a2 is equal to 1. This is the first equation I'll get. Minus 6a2 plus 2a1 is equal to 2. This is the second equation I'll get. And 2a2 is equal to 1. This is the third equation I'll get. From this equation, I can directly say a2 is equal to 1 by 2. From this equation, I can say a2 is equal to 1 by 2. Now this a2 I can substitute over here and find out the value of a1, and then a1, a2 I can substitute in this equation and I can find out the value of a0. So you can solve them on your own and you will get the values. A0 is equal to 9 by 2, a1 is equal to 5 by 2, and a2 is equal to 1 by 2. So now the particular solution becomes ARP becomes 9 by 2 plus 5 by 2 r plus 1 by 2 r square. Now we know that homogeneous solution, what was the homogeneous solution? ARH. Homogeneous solution was B1 2 to the power n or 2 to the power r plus B2 3 to the power r. Now we know that the general solution AR is the sum of ARH plus ARP. So that gives me B1 2 to the power r plus B2 3 to the power r plus 9 by 2 plus 5 by 2 r plus 1 by 2 r square. So this is the solution of the recurrence relation. Remember, there was no initial term, so we are not going to find the value of B1 and B2. So I hope I have been able to make the solution of the recurrence relation, particular solution, a little bit easier for you. Now my suggestion is, get hold of any book or any practice sheet, solve as many questions as you can, and only then will you be able to properly and easily solve the questions without mistakes. Solve as many questions as you can, right? Remember the table that we talked about, the trial function table, that you have to remember. That table must be there on your tips. Only then you will be able to identify the trial function immediately by looking at the FN. So till the next time, thank you.